To begin with atmospheric thermodynamics, we must first derive the ideal gas law, also known as the equation of state. The equation of state is an equation that relates thermodynamic state variables, or volume, temperature, and pressure, in a single equation. This will be important later for weather prediction models and such. To start with the derivation, we must first know four basic laws. The first two is called the first and second law of GL, where GL is the initials of a French thermodynamics researcher who found two relationships. They found when holding pressure constant that volume was directly proportionate to temperature T by a constant alpha times the initial volume, V naught. And holding temperature constant, pressure was directly proportional to temperature by a constant beta times the initial pressure. Then we have Boyle's law, which shows when you hold temperature constant, P times V, while P and V are changing, the multiplication of P times V will stay the same at a future time. And that is another way of saying that P is inversely proportional to volume by a specific amount, which will allow this to stay true. And finally, Avogadro's law says that volume is directly proportionate to the number of moles with a constant lambda, my bad. So to start the derivation, we take a system with a certain pressure, volume, and temperature, and we move the system in time while holding volume constant, to a different pressure and a different temperature. We can then start with Boyle's law, where we have pressure is equal to alpha over V. We can multiply V on both sides, and we will get PV is equal to alpha. Then we can use the first and second law of GL, multiplying by P over T and V over T, as we see above, dividing on both sides, the T, we will get these constants out. So we will be left with these constants, and then also the alpha term here, because we're multiplying these to this side, so these are extra. Then combining like terms, we get that PV over T squared is equal to this constant. Then we can take the square root on both sides. We'll be left with PV over T is equal to this messy constant. And we can call this constant A for simplicity when writing. We can then use Avogadro's law, which says volume is equal to lambda times N, adding that to the right side of the equation to correct this volume. So this volume here is technically not the same, not exactly the same, because we've applied this to both sides. And now we're left with P over T is equal to A lambda N, and we can say that A lambda is equal to R, where we will call R the universal gas constant. That gives us the equation PV equals nRT, as you may have seen before. However, this is for any specific gas. It's not, in atmospheric science, we're very interested in a specific gas, not a general gas. Or an ideal gas. So while still assuming that it is ideal to get this equation, we can then say that the specific gas constant Rg, where G stands for gas, is equal to universal gas constant R divided by the molar mass of that gas. And we can then multiply mg on both sides to get R is equal to mg Rg. And we can notice that mg times Rg is actually mass, because we have the number of moles times kilograms per moles. The moles cancel out, and we're left with kilograms. So that gives us the equation PV equals capital M for mass RGT. And this will be our equation of state, generally. But in atmospheric science, we're interested in RD, which is the universal gas, the gas constant for dry air. So D stands for dry air. And we know that the universal gas constant is, sorry, let me correct this. RD, this could be the dry air gas constant. We know that R is equal to 8.314 joules per moles per kilogram by laboratory experiment, as well as the molar mass of air, 2.9 times 10 to the negative 2. And also note that this air is not just oxygen, it's including other gases as well, because for oxygen, we would get a slightly higher number of 3.2 times 10 to the negative 2, rather than 2.9 times 10 to the negative 2. And doing this division, we will get that RD is equal to 287 joules per kilogram per Kelvin. And that will leave us with the equation PV equals mR dt. And now we note that density, which is defined as the mass per volume, which is the same as thinking of a bunch of molecules inside of a certain volume, the density would be per specific volume in this area, how much is in that specific volume. And so we can divide V on both sides, and we will get a term that is equal to M over V, which is equal to rho. And we're left finally with the equation that is used in weather prediction models, which is pressure is equal to density times R dt. And for some of these models, we also include an ocean system. And since water has a different molar mass than air, we will use W, RW, and making this calculation using 1.8 times 10 to the negative 2, the molar mass of water, we will find that RW is equal to 461 joules per kilogram per Kelvin, as compared to for dry air, which is 287, so we have a slightly higher constant here. That means that as temperature increases, pressure will actually increase more because the constant multiplied by temperature is larger. And that will give us an equation P is equal to rho RWT for the ocean system. And so we can have things going on in this ocean system that affect the system above in the atmosphere. And that will be all for today. And next we will be discussing what I call the thermodynamic relationship, which will be later useful for deriving the thermodynamics equation. So stay tuned for the next video.